we saw that we could start solving differential equations using the substitution rule from Calc 2. Recall that the substitution rule says that the integral of f of v times dv dt dt is equal to the integral of f of v dv. Now let's return to the example where we modeled the velocity of a falling object with the differential equation dv dt equals 9.8 minus v over 5. Recall that we looked at the direction field of this and found the equilibrium solution, but we didn't find any other solutions. But now we can find the solutions for the velocity of that object. Like with the last example, we'll use this substitution rule. And in order to use the substitution rule to integrate the left-hand side, we need to write it as a function f of v times dv dt. So we can't simply add v over 5 to both sides. What we want to do is combine the right-hand side into one term, using a common denominator. Doing this, we'll rewrite the right-hand side as 49 minus v over 5 by multiplying 9.8 by 5 over 5. Now we can divide both sides by 49 minus v, and this gives us 1 over 49 minus v times dv dt is equal to 1 over 5. And we've written it in a form that we can use the substitution rule once we take the integral. So we'll integrate both sides with respect to t and have the integral of 1 over 49 minus v times dv dt dt is equal to 1/5 dt. Writing it this way, on the right-hand side, we can directly integrate 1/5 dt to get t over 5 plus c. While on the left-hand side, we can use the substitution rule to get that the integral of 1 over 49 minus v times dv dt dt is the integral of 1 over 49 minus v dv, which integrates to the natural log of 49 minus v. To do this integration, we'd make a substitution u equals 49 minus v and proceed from there, though we won't do that in this video. So we've found that the solutions of our differential equation satisfy negative the natural log of the absolute value 49 minus v is equal to t over 5 plus c. I'd like to note here that there should have been a constant of integration on the left-hand side as well. But as we did in the last example, we can combine both constants of integration on one side. Moving forward, we'll likely only write the constant of integration from one of the integrals. So now we have an algebraic equation rather than a differential equation for v. To solve this algebraic equation for v, we'll multiply both sides by -1 and exponentiate to get the absolute value of 49 minus v is equal to e to the negative t over 5 plus c, which can be split up as e to the negative c times e to the negative t over 5. Resolving the absolute value, we can rewrite this as 49 minus v equals plus or minus e to the negative c times e to the negative t over 5. And plus or minus e to the negative c is just some other constant that we'll call lowercase c. And this gives us that 49 minus v is equal to lowercase c times e to the negative t over 5. And then subtracting 49 and multiplying by -1 on both sides, we can conclude that v equals 49 minus c times e to the negative t over 5. Moreover, since c is some arbitrary constant, we can simplify this to v equals 49 plus k times e to the negative t over 5, where k is just negative c, to make our solution look a little nicer. I want to take a moment to line this up with what we saw in the direction field as well. Using the direction field, we found that the equilibrium solution was v equals 49. This happens when k equals 0 in the family of solutions we found here. Moreover, if k is not 0, the term k times e to the negative t over 5 will go to 0 as t goes off to infinity, because e to the negative t over 5 will be going to 0. So for every solution, no matter what the value of k is, the long-term behavior of V is that it'll tend towards 49, which again is the conclusion we drew from looking at the direction field and analyzing that equilibrium solution. It's good to see that what we found algebraic here lines up with what we saw geometrically in the direction field.